Hi, this is Calculus 12, Chapter 7.1. We're going to look at integral as a net change. This is already something you know, but we're just learning it more formally. So, if we do the definite integral from a to b, then we can look at this as being the net change. So for instance, if we were looking at a velocity time graph, this would be the change in displacement over the time A to B. Or you could look at it as the change of distance from the time A to B. Okay, we've done this before, vector quantity, and it's a measurement that has direction. This means it can be positive or negative. And we've done this before, so I'm not going to go over this. And we've done scalar quantity. It's a measure without direction. And it's always a positive value. Okay, for instance, distance. Let's recall area under the curve is the integral of the absolute value of f of x dx. So for any scalar quantity, we have the integral of the absolute value of f of x dx. And if you're doing it algebraic with definite integrals, you need to find the zeros of f of x. That way we can partition. That way we can add the negative of the definite integral below the x-axis. Okay, here's an example. Exercise 1 to 8, we're doing number 2. We're given the function v of t as the velocity in meters per second of a particle moving along the x-axis. Use analytic methods to do each of the following. Determine when the particle is moving to the right, to the left, and stop. Find the particle's displacement for the given time interval. Find the total distance traveled by the particle. And for number 2, we have v of t is 6 sine 3t. And for the period 0 to pi over 2. We'll note that when solving for v of t equals 0, we have zeros for sine, at k pi, where k is from the set of integers. So zeros for sine 3t is at k pi over b. And we're noting that b equals 3. So this is k pi over 3. And on this interval, we have 0 and pi over 3. And just a refresher for trig, we have that. This is pi over 3. This is 2 pi over 3. That's outside of our given domain. So we're only concerned about these two zeros, and this is pi over 2. Therefore, we're moving right. V of t greater than 0. And in general, it would be 2n pi, or 2 pi n, over 3 is less than t is less than 2n plus 1 pi over 3. And instead of integers, that means we have t belonging to 0 pi over 3. And we're moving left. when v of t is less than 0. So that's 2n plus 1 pi over 3 to 2n plus 2 pi over 3. And that means we have t in the interval from pi over 3. And here we need to put a square bracket, okay, because it's inside this interval. It's not on the boundary of the interval. Okay, that answers part A. Part B, we want to find a displacement function. So s of x is the integral from 0 to x of 6 sine 3t dt. You have negative 6 cos 3t over 3, and we're going from 0 to x. That means we're doing negative 2 cos 3t from 0 to x. And we substitute, we get negative 2 cos 3x minus negative 2 cos 0. And that gives us 2, 1 minus cos 3x. You can write it like this, or you can write it like 2 minus 2 cos 3x. It doesn't really matter. They're simple enough that either one is fine. Now we have our displacement function. We can just substitute our limits of integrand. S pi over 2 minus s of 0, 2, 1 minus cos 3 pi over 2. Remember, we're doing 3x, 3 times pi over 2, minus 2, 1 minus cos 0. That's 2 times 1 minus 0, minus 2 times 1 minus 1. That's 2 meters. Please don't forget your units. And if we're doing distance, we have s of pi over 3 minus s of 0 minus s of pi over 2 minus s pi over 3. We can simplify this. We have a minus minus, so this is 2s pi of 3 minus s of 0. We've already calculated s of 0 here, and that's 0. And minus s of pi over 2, that's 2. So we just have to calculate this. So this is 2 times 2, 1 minus cos 3 times pi over 3, that's just pi, and a minus 2. So this is 4 times 1 minus cos of pi, that's negative 1, minus 2. So this is 8 minus 2, and that's 6 meters. Let's look at our next problem, Hooke's law. Hooke's law applies to compressing springs and also applies to stretching springs. That is, it requires a force kx to compress a spring a distance of x from its natural length. Suppose a 10,000 pound force compresses a spring from its natural length of 12 inches to 11 inches. How much work was done compressing the spring half an inch and the second half an inch? So, looking at our diagram, this is our spring. we have 12 inches, and we're compressing it to 11 inches. And this is our y direction. Okay, so work is defined as the integral of the force integrated over the distance. And we want to note that K is in pounds per inch, and this is in inches, and this is in inches. And when we integrate, we're going to get pounds per inch times inch squared. Cancel, cancel, and we get our units as inch pounds. Okay, we integrate this. This is not difficult. We have K x squared over 2, and we're going from 0 to y. That gives us ky squared over 2 minus 0. So we just have ky squared over 2. And because we're squaring y, we don't need the absolute value. And k will be positive. That's the work equation. Now we have the force equation. And this is the work equation. We need to solve for k. So we know that k equals F over the absolute value of x. And the force is 10,000 pounds. And we are going -1 inches. And we're doing the absolute value of x. So this is just 10,000 pounds per inch. Okay, this is still A. So W of 1/2, we have 10,000 over 2 times 1/2 squared. Gives us 5,000 times 1/4. And that's 1250. And we need units. We already computed the units up here. That's inch pounds. And part B, and we can think of this is our integral from 0 to 1/2. Now we're doing the integral from 1/2 to 1. We have W of 1 minus W of 1/2. W of 1, we have 10,000 times 1 squared over 2. So that's 5,000 inch pounds. And sorry, we have a minus W 1/2. And that's minus 1250 inch pounds. So our answer is 3750 inch pounds. Let's look at another example. Oil flow. Oil flowing through a cylindrical pipe, radius 3 inches, and there's friction from the pipe, and that slows the flow along the edges. And the speed at which the oil flows at a distance r inches from the center is 8 times 10 minus r squared inches per second. So we have fast flowing and slow flowing at the edge. And this happens in other situations, such as water flowing along a river. You'll see that the water moves slowly at the edges and it moves faster in the middle, although this is going to be a different formula. Okay, in a plane cross-section of a pipe, a thin ring with thickness delta r at a distance r inches from the center approximate a rectangular strip when you straighten it. What is the area of the strip and hence the approximate area of the ring? Okay, so we've done this before. C equals 2 pi r, and we make a small cut of this thin ring, straighten it out, and we get approximately a rectangle, 2 pi r delta r. This is ds dt. Now for part B, dv dt based on r is ds dt times a. So we get that from there, and we get that from there. And this works out to 8 10 minus r squared and 2 pi r delta r. And this is a slight error. We're integrating a Riemann sum, dv dt of r dr. Oops. And when we change that to an integral, 0 to 3, we have this, and then this delta r becomes dr. So we have 8 10 minus r squared 2 pi r dr. And then let's integrate this. This should be straightforward. 16 pi. We're just taking the 2 times pi times 8. And now we're integrating from 0 to 3. 10 r minus r cubed dr. 10 minus r squared times r. And we have 16 pi. Integral of this is 10 r squared over 2 minus r to the power of 4 over 4, and integrating from 0 to 3. We'll substitute this in. 16 pi 5 r squared, that's 9, minus 81 over 4, and that's 1, and we subtract off 0. So we have 16 pi 45 minus 81 over 4. Common denominator, we multiply by 4, that gives us 180 minus 81 over 4. This is 99. 16 divided by 4 is 4. 4 pi times 99. And that gives us 396 pi. And our units is volume, so inches cubed per second. So what you want to imagine is an area of a pipe, and it's flowing along in a direction. And when you make it flow along in the direction, you get a volume. Now, our lower limit of integration is usually 0, but use whatever you're given. Such as our spring example where we wanted to find the work done in the second half inch. So we're integrating from a half to 1 rather than 0 to 1. And that completes this lesson.